What we're going to do in this video is we're going to look at the idea of markers or memory flags in PLC programming, and we're going to look at how they're incorporated when we're doing things like sequences. So sequences can come in a lot of range of I suppose different physical outputs, but what I mean by sequences for this particular application is if we have two cylinders, which you can see here, say cylinder A is on top, cylinder B is on the bottom, and what we're going to do is we're going to do an extension and retraction of both cylinders, but in a particular sequence. Okay. Now the sequence we're looking to do is that the cylinder on top, cylinder A, is going to extend. Then once that is extended, B is going to extend. Then B is going to retract, and then A is going to retract. So that's the sequence we're looking to do, and we're going to talk through how we may set that up. We're not going to go into the full solution of it, but we're just going to kind of build it up until this kind of key point where we need to add in some memory or a marker and how we can use that. Now there's you'll see some tags here, so this is just kind of a setup we've got. Don't pay too much attention to the types of inputs and outputs that are here. Just assume for the fact that we've got an electrical roller switch at the end for each cylinder to sense its extended and retracted position, and then ultimately I can turn on a solenoid to either side of the double acting cylinder to either extend or retract the cylinder. So I can put air into here to force the cylinder out, or I can turn on a solenoid that will put air into here to force it into retraction. Okay, so you'll see ultimately we've got some inputs which are sensing our position and telling us where we are with the cylinders, and with some outputs that are actually going to move the cylinders for us. And then what you'll be able to see is you'll ultimately be able to see as I click through the images the sequence I wanted to do. So here you'll see A is extending, then you'll see B extending, then ultimately B coming back, and then A returning, which ultimately gets us back to our starting position. Okay. So in our TIA portal, all I've done so far is I've created an input table, and I have my sensors there to sense when this A cylinder is at its minimum position and maximum position. So you'll see that's I0.0 and 0.1, and the same for B. Our sensing positions for the minimum and maximum positions, and then you will see ultimately our outputs are what forces our cylinder A to extend, A to retract, B to extend, and B to retract, and they are cues, and you'll see that from the image there as well. So if we just look at this at a very basic sense, okay, we go into our code. Our starting position is this here, both cylinders fully retracted, and ultimately two inputs are going to be activated, and we're assuming these are normally open inputs, and those two inputs are going to be activated, which allows us to start our sequence. Okay, so we can nice and easily add in our two inputs, which is ultimately going to be when A is at its minimum and when B is at its minimum. That will give us the trigger to start our sequence, which we want A to go ahead and extend. Okay, so that's just all I've done there. So when those two inputs are triggered, that means we're in the rest position, so we can go ahead and put power into Q0.0 so that A can start extending. So we take that type of an approach and we look at our next step. Well, in this step you'll see this input and this input are now triggered, are now active. So that will help ultimately influence our next step. So you could, if it allows you to copy and paste networks, does it? Can I copy that network? Copy, and not to worry. Okay, so our next two inputs that's going to ultimately trigger our output in this sequence is A is going to have extended, B is still going to be at its minimum position, and that is allowing B to go ahead, and extend. So just delete that. It's the wrong. That's an input. So B can go and extend out. Okay, so all we're saying here, once these two are triggered, we can go ahead and turn on Q0.2, which will allow air to go ahead and extend B out. And that's what we've got there. Then when we get into our next step, B has extended, A is extended, so these two inputs are going to be active. So we can go ahead and put that in. So A will have extended, B has extended, and what we're looking for there now to do is going into our next step, which would be for B to go ahead and start retracting. Okay, and then when B retracts, we've got our setup. These two inputs are triggered, which will then allow us to put A back. Okay. So what we have here in this setup is A max still triggered. We're now B min. Sorry about that. And then that's to ultimately tell us A to return home. And that's essentially our sequence. A extends, B extends, B retracts, and then A retracts. Okay, and we've looked through that, and we're back to the starting position ultimately, and we've seen how it loops through. But there's an issue here. Okay, well, what's going to happen is if we look at two lines in our ladders, okay, if we look at when B is extending, okay, we have A max and B min, and when A is retracting, we have A max and B min. So ultimately, we've got the same inputs. It's going to trigger, okay, two different outputs. But what that's going to do is it's going to get confused in our sequence. And as you can see this position here is the exact same as this position, this step. So what happens is the PLC gets confused. It doesn't actually know which part of the sequence we're in, and therefore doesn't know which step to go on to, whether it should go on to step 4 or whether we're still on step 1 and we're supposed to be moving on to step 2. And we've no other inputs that can influence the system, and we don't want to buy new inputs because they may be very expensive. So how do we go about that? Well, what we can do is we can use some internal memory to tell the PLC where we are in the particular sequence that we're going through, and ultimately which step we're on. So if you look at this, what we're going to do is, and you could add ultimately memory to memorize each step, but what we're going to do is we're going to just look at adding in a memory table, okay, and we're just going to add in one bit of memory just to show you what could be done. So I'm going to add in a memory bit, and we're going to call it I'll just call it memory. Think of a good name. We'll just call it memory for the step. Okay, so we're memorizing a particular step. Now when we're adding in memory, we need it to be M. Okay, and we'll just start it in our starting table, starting positional table. So we have a memory bit that I'm going to use. Now remember, memory can be inputs and outputs. Okay, so what am I going to say? Well, if I look at this position here, okay, we go out and we extend out. What do I want to memorize when we're going from step 1 and ultimately at step 3? The thing we want to memorize is a step in between, that B has gone on out and extended out, that we've completed that, ultimately that position, that step. Because if we get back to this position and we know we've completed the B extension, well then yes, we're supposed to go to step 4. So ultimately we're trying to remember step 2, so that when we go to step 3, we know we're moving to step 4 and not ultimately back to step 2 again. So hopefully that makes sense. So we're trying to memorize, we're trying to turn on a memory bit when step 2 occurs. Okay, when this comes out and it's triggered. Because then what we can do is we can use that memory bit as an input to tell us when to activate a particular step. Because if you watch me go through this again, so starting condition, A goes out and extends, no memories on. B goes out and extends, we turn on a memory bit. Now when we get to this part, we can use these 2 inputs and that memory bit to then give us a unique piece of code to send it home. So if we were going to kind of code that up, what we would do is, so we've step 1, we've step 2, then what I want to happen is, if I can just add in a new network in below here, I'll keep it in there. I just come in below here and I add in a new line. And I want to memorize that ultimately the B has gone out and extended and turned on a memory bit. This memory bit. So when B goes out, it hits the input that tells us B is extended. So when it comes out here, it hits I 0.3 and it turns on our memory bit. Now we need that memory bit to ultimately latch on so that we can ultimately memorize that for the rest of the sequence, that it has gone on and has stayed on. Now we're going to have to turn that memory off when we ultimately get back to the start of our sequence. So what ultimately tells us we get back to the start? Well, if we look at our second last step, the input that tells us we're back at the start would be I 0.0. So we can put that in as A min. So what I've done just after this step here, when B goes and extends, when B max gets hit, so after B goes and extends, B max gets hit, what I've done is I've latched on a memory input. Okay. So what that allows me to do is, right, B can go ahead and return, and when we get down to here, I can use that memory bit as an input now to my system to tell me we can go ahead and A can return. Okay, and I also need that to be in here to completely make this completely different. Put my memory bit on, because that needs to influence the line of code as well. So if we don't put it in there, well, you know, if A min and A max and B min are still hit, B will go ahead and extend. So what we're trying to stay is now, if we look at step 1, so we've just 2 inputs are triggered, we go ahead and extend A. A comes out, and when it hits A max, our memory hasn't been turned on yet, so B can go ahead and extend. When B goes ahead and extends, it turns on a memory bit that stays latched on. Because now when we retract B, and we go ultimately to retract A, we can use this, the fact that this memory bit is now on, that will allow power to go to the retraction, and it won't get confused up here, because if this memory bit's on, that will be opened and B will never extend out again. So that allows us to go through the sequence, get to step A, B's allowed to extend out because no memory's on. Now the memory's on, so B will never be allowed to extend back out again, and ultimately A will come home. When A finally comes home, it unlocks that latch so that our sequence is able to recycle our sequence again. Okay. So I know it's been a long video and it can be a bit of an awkward procedure to understand, but what we're trying to do is hopefully you can spot that 2 of the steps in our sequences, ultimately step 1 and step 3 are the exact same. And because of the limited number of inputs we have, we need to introduce memory so that we can create a new scenario so that the PLC doesn't get confused. Because ultimately the PLC doesn't know, unless we give it the memory, what step in the sequence it is. And that's why we use them memories. Memory bits, or some people call them flags, to ultimately flag that a part of the sequence has happened. And the memory bits are just used just exactly like inputs and outputs. We just have to latch that bit of memory on so that that stays, and we ultimately memorize that that step is completed the whole way through the cycle until the cycle is finished. Then we reset our latch so that we can start the cycle again. Now the code may not be completely bulletproof because, again, depending on the outputs and the inputs you have, you may get a different solution. So if the output needs to be latched on to allow the cylinder to go ahead and fully extend, well, that'll change your coding ever so slightly. Same way, depending on how you wire up your inputs, we're assuming these are all wired in as normally opened. But you get the idea, and hopefully it shows you an area of where the memory plays an important role. So we use these %M tags as memories. We can also use them as organizational tags. You see them in other videos where we use the M to ultimately structure or organize parts of our code. And yeah, we can use them as memories, and the inputs and outputs are dummy outputs that we call them, or dummy inputs, because they're actually not physical. They're all internal into the PLC. So that's where markers can be used in a sequence. This is a common sequence that can be used for like a pick and place. So hopefully makes a bit of sense, and you've enjoyed this video.